Hello everyone, this is Dr. Lennon and welcome to the Test 1 review. So this first one focuses on the fundamental theorem of calculus part 1 that basically says that the derivative and integral are inverse operations. So for this one we're integrating from 1 to x cubed of dt over t squared plus 15. So basically what we do is we just replace the t by x cubed, but then we additionally have to multiply by the derivative of x cubed. So this is going to be essentially x cubed, the derivative of that, times 1 over x cubed quantity squared plus 15. And we can put that all together. So the derivative of x cubed is 3x squared. And then on the bottom we're going to have x to the 6th plus 15. And that is it. So you just basically have to remember that they're not only inverse operations, but if one of the limits happens to be a function of x, you also, from the chain rule, have to multiply by the derivative of that quantity as well, that function as well. So let's go ahead and move on to the next one. Okay, so for the second one, we have to find an antiderivative, and we're going to go ahead and use a u substitution to do that. So you can tell that when you take the derivative of something raised to the 6th power, you'll end up with something raised to the 5th power. So we're going to let u be what's in the denominator there. So let u be 1 minus 6x to the 6th. So du will be, let's see, negative 36x to the 5th. So we really just want to solve for the x to the 5th, so du over minus 36 will be x to the 5th. And so then we can replace these things in the original integral. So we'll end up with the integral of 3x to the 5th over the square root of u times du over negative 36. So that will leave us with negative 1/12 on the outside. Sorry, I forgot the x to the 5th. So the x to the 5ths will cancel. Those will go away. And we'll have the integral of 1 over the square root of u du. So that will be basically 1 over the square root of u is u to the negative 1/2. So if you add 1 to the power, it will be u to the 1/2. And then you'll be dividing by 1/2, which will be multiplying by 2. So we'll have negative 1 over 6, the square root of u plus c, which will be negative 1 over 6 times the square root of 1 minus 6x to the 6th plus c. And that is essentially the end of it. If we had a definite integral, we could switch the limits and just finish with a numerical answer. But in this case, we want to switch back to the original quantity in terms of x. Okay, so for number 3, we have another u substitution. We want to let u be the tangent of x because we know the derivative of the tangent is secant squared. So if we let u equal the tangent of x, then du will be the secant squared of x dx. And that will allow us to solve for this, at least replace this integral in terms of u. So we'll end up with the integral of, so du will take care of the secant squared of x and dx, so we'll have du over u to the 6th power. So that's u to the negative 6th power, so basically we're going to end up with negative 1/5 u to the 5th power plus a general constant. And if we want to change back to the original variable in terms of x, u is going to be replaced by tangent of x. So we're going to have negative 1/5 tangent to the 5th of x plus our constant. And that's it. So again, nothing different from the previous one. We're just dealing with some elementary formulas that involve trig functions. Oh, sorry, I've just noticed there's one small error. It should be u to the negative 5th, which would make it tangent to the negative 5th of x plus a constant. So if you want, what we can do here is we can change that to 1 over, so this would be minus 1 over 5 tangent to the 5th of x plus c. So that negative exponent, you can also put it in the denominator. So it's important to recognize that that is in the denominator and make sure the negative exponent is properly placed. So sorry for that, but it is correct in its current form. Okay, so this third example is an integration by parts. So let's just recall the integration by parts formula. It's uv minus the integral of v du. So in this case, the thing that's easier to differentiate is the natural log. So what we're going to do is we're going to let u be the natural log of x. So that would make v be x squared. So du will be 1 over x, and we want to make dv be x cubed. So v will be the antiderivative x cubed over 3. So our integral will become uv, so that's the natural log of x times x cubed over 3 minus the integral of v times du, which will end up as x squared over 3 dx. So that has a pretty easy antiderivative. It's natural log of x times x cubed over 3. The first term remains the same, and then we're going to end up with minus x cubed over 9 plus our constant from integration. So again, it's just recognizing that when you have the product of two different classes of functions of x and you want to take their antiderivative, that's going to be an integration by parts. Okay, so for this next one we have a trigonometric substitution. So again, you can appeal back to that section and realize that basically there's three kinds of subs, one for cosine, one for sine, and one for tangent. So in this case, we're going to be replacing using sine. So what we're going to do is we're going to let x be 9 times the sine of theta. So dx is 9 times the cosine of theta. So what happens is our integral up here turns into the integral of 9 cosine theta d theta on top, and on the bottom we're going to get the square root of 81 minus 81 sine squared theta. And again, you want to check what your limits do. So our limits, 0 will just stay 0, and 9 square root 3 over 2 as an x value will change into pi over 3 as a theta value. So our limits will be going from 0 to pi over 3. So this will end up actually as just the integral from 0 to pi over 3 of 9 cosine theta, and the bottom will end up with, from the Pythagorean identity, the square root of 81 cosine squared theta, which will come out to 9 cosine theta d theta. So really what we have is just the integral of, 1, which is going to change back into theta. So we have the integral of theta from 0 to pi over 3. And so this just comes out to exactly pi over 3. And that's it for this trigonometric substitution. Okay, so for number 6 right here, what we have is a partial fractions decomposition. So remember what we want to do is we want to take this 42 over x squared minus 49 and factor it, which looks like 42 over x plus 7 times x minus 7. And we want to write that as sum a over x plus 7 plus some capital B over x minus 7. So what we do is we basically multiply both sides by x plus 7 times x minus 7, and we end up with 42 equals a times x minus 7 plus b times x plus 7. And so what do we get? We get a system of equations. Basically our a plus our b has to be 0 because there's no x value on the left side of the equation. And then we have our constant value. So minus 7a plus our 7b has to be exactly 42. And then we can solve that with whichever method of solutions of system of equations that we want. So basically we know a has to be equal to negative b, so I'm just going to plug that into my bottom of equation. So I'm going to get 7b plus 7b equals 42. So I end up with 14b equals 42. So I know that b is equal to 3, which means a is equal to negative 3. So now we can go back and rewrite our integral using that fact. So essentially our integral, what was it, from 0 to 1? Let's double check that. So it was from 0 to 1 of 42 over x squared minus 49 dx. This is actually just going to be equal to the integral from 0 to 1 of negative 3 over x plus 7 plus 3 over x minus 7 dx. And each of those can be just done using the natural logarithm. So we end up with the integral of negative 3 natural log x plus 7 plus 3 natural log absolute value x minus 7 from 0 to 1. And so let's see what that is. We've got some absolute values there, so we get negative 3 natural log of 8 plus 3 natural log of 6, since we're taking the absolute value, minus negative 3 natural log of 7 plus 3 natural log of positive 7 again. So I don't know how much that can be simplified. Probably you can put it all together as one big logarithm if you want, but I doubt if you have to. So let's go. So we'd have negative 3 natural log of 8 plus 3 natural log of 6 plus 3 natural log of 7, and then minus a 3 natural log of 7. So these two cancel out, and we just end up with negative 3 natural log of 8 plus 3 natural log of 6 for this one. Okay, for 7, we want to find the position and velocity along a straight line given the information. So we know the acceleration, so we want to find the velocity. Again, we know the acceleration is just going to be the antiderivative plus whatever the initial velocity happens to be. So you can look up those formulas if you want, or you can just use the integration. But basically, v of t is going to be equal to v of 0 plus the integral of a of t dt. So that's what we're getting here. So our velocity is that v of 0, 9 plus the antiderivative of the sine of pi t, which is just a u substitution with pi t, so that should just be sine of pi t over pi. And then we're going to repeat the same thing with the position. Okay, so I've botched this up a little bit. So let's go ahead and just go step by step. So v of 0 is in fact 9, but as we see, a of t is equal to the sine of pi t, and we're integrating from 0 to t. So that's what we need to keep in mind here. So we're going from 0 to t. So we're doing the integral from 0 to t of the sine of pi t dt. And so this is going to be 9 minus 1 over pi times the cosine of pi t from the chain rule. And this antiderivative is going to be from 0 to t. So what that is going to leave us with is 9. When you plug in 0, we're going to get plus 1 over pi. So 9 plus, because we're going to be subtracting 0, so I'm going to write the plus 1 over pi first. And the first thing we plug in t, we're going to get minus 1 over pi cosine of pi t. So minus 1 over pi cosine of pi t. Okay, so that's it. And then the position is going to follow a very similar thing. We're just going to iterate one step, right? So we know the position s of t is now just going to be v of 0 plus the integral from 0 to t of v of t dt. So we're just iterating one more step along the way. So let's go ahead and do that. Okay, so one small thing, it should not be v of 0, it should be s of 0, so let's go ahead and replace that. Okay, so then let's go ahead and continue. So s of t here, s of 0 is 8, and then we are integrating from 0 to t, and we're using what we found in the previous part. So we're going to be integrating 9 plus 1 over pi minus 1 over pi cosine of pi t dt. Okay. So let's see what we end up with here. So we know that we're going to get 8, and then we're going to do the rest of it. So we're going to get essentially 9t, or I guess supposedly this should all be an x, but it doesn't really matter so much. 9x plus, we can kind of do it all in step, 1 over pi t, and then we have to do the same thing here. So the antiderivative of cosine here is going to be sine, so we're going to get 1 over pi squared cosine of, sine of pi t and then we're going to want to subtract whatever we get when we plug in 0. Oh no, and then this is from 0 to t. So that is the antiderivative. Then we're going from 0 to t. And when we plug in t, we're going to get all of this stuff. So 8 plus 9t plus 1 over pi t minus 1 over pi squared sine of pi t. And then when you subtract 0, the 9t is going to go away, the 1 over pi t is going to go away, and the sine of 0 is also going to go away. So that is your answer for the position function that we're looking for there. So that's it for that one. Again, just be a little bit careful, but really not so difficult. Okay, so for number 8, we're looking for the area of the shaded region, and we're going from top to bottom. So we want to figure out where they intersect first. So the points of intersection can be found by setting 3y equal to y squared minus 4, and then we can get everything on one side of the equation and factor. So not so bad there. We get y minus 4 times y plus 1. So our answers are y equals -1 or y equals 4. So that is where we are, those are our limits of integration. And then again, we want to use the right radius minus the other radius. So our area here is going to be the integral from -1 to 4. And then we're going to be taking the line 3y minus the parabola y squared minus 4. So I've kind of botched that up a bit. I've written it. Y squared minus 4, and this is what we want to integrate with respect to y. So we're integrating from -1 to 4. Of minus y squared plus 3y minus plus 4, two negative signs, dy. And then let's go ahead and integrate this, and that'll give us the area between the two curves. So we're getting minus y cubed over 3 plus 3y squared over 2 plus 4y from -1 to 4. So we want to plug those numbers in. So this comes out to 56 over 3, and then plus 13 over 6, which is, well, this one actually asks for a decimal answer, so you can respond to 2 places. This is about 20.83. So that's it for this one. So we'll go ahead and use the slicing method here, but in general, this one actually can be done using geometry. So one thing to note, if we're looking at the solid found by revolving this thing about the x-axis, we actually do have some symmetry here, because essentially your picture, in this case, we have a semicircle of radius size 7, so we've got something like this, where this is set minus 7, this is 7. So we can actually integrate from 0 to 7 using, and then just doubling the result. So the volume here is going to be 2 pi times the integral from 0 to 7 of this square root of 49 minus x squared dx. So what do we get? Well, we're getting 2 pi times the integral from 0 to 7 of 49 minus x squared dx. So let's go ahead and continue. So that's going to be 2 pi times the antiderivative, which is going to be 49x minus x cubed over 3 from 0 to 7. So that's going to be 2 pi times 49 times 7, which is going to be 343 minus 343 over 3. And so what is that going to be? That's going to be 2 times 343 over 3 times 2 again. So, oh, I don't know, that's going to be 4 pi times 343 over 3, which we can do on our calculator here. 4 times pi times 343 over 3 is about 1436.76. And that's going to be units cubed. And then you can also check from geometry just to double check this. So from geometry, the volume of a sphere is 4/3 pi r cubed. And that's exactly what we're getting here, right? We're getting 4/3 times pi times 7 to the 3rd power, which, you know, is 1436.76 units cubed. So our calculus reaffirms what we learned in geometry in this example. All right, so on to the last one. Okay, so the last one is a surface area problem, and remember the surface area formula is essentially the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So in this case, what we have going on is we're doing everything with respect to y. So everywhere we see an x, we're going to place that using something in terms of y. And so the first thing we want to do is find the derivative. So essentially x prime is going to be what? Well, it's going to be the derivative of the inside, which is 14 minus 2y divided by, so it's a 1/2, so there's going to be a 2 on the bottom, times the square root of 14y minus y squared. The 2 can be divided into the numerator, so we can write that as 17 minus y over the square root of 14y minus y squared. So then our surface area here is going to become the integral from 2 to 3 of 2 pi times our function, the square root of 14y minus y squared, times the square root of 1 plus this derivative squared. So 1 plus the derivative we just found, quantity squared. So 7 minus y over the square root of 14y minus y squared, quantity squared dy. Okay, so we're hoping for a bunch of cancellation eventually, but let's go ahead and see how that's going to work. Essentially, we're going to need to get a common denominator in the second square root, so we're going to end up with 2 pi integral from 2 to 3. We've got the square root of 14y minus y squared, and then we're being multiplied by what's happening there. We're going to get a gigantic square root, and we want to make a common denominator. So when you square it, we're going to get a 14y minus y squared over 14y minus y squared. So that's our 1 we're replacing. And then we're going to get a plus 49 minus 14y plus y squared, foiling the numerator, over 14y minus y squared, and all of this is being multiplied by dy. Okay, yeah, it looks like a big mess, but we're going to get some cancellation because already we can tell the 14y and the minus y squareds are going to cancel. So this is going to become 2 pi integral from 2 to 3 of the square root of 14y minus y squared times the square root. Again, when you add the common add the fractions using the common denominator, we're only going to end up with a 49 on top, and over here we're going to end up with the 14y minus y squared, and that's it. So what's going to happen is we're going to get our cancellation that we want. Essentially, the square root of 49 is going to be 7, so we're going to end up with 2 pi times the integral from 2 to 3 of the square root of 14y minus y squared times 7 over the square root of 14y minus y squared. So those go away, thankfully, which makes everything much easier. And then we're getting the antiderivative is just going to be 7y, so we're going to get 2 pi times 7y from 2 to 3. So that's going to be 21 minus 14. So we're just going to get 7 times 2 pi. So our answer here should just be 14 pi. Again, that is a surface area, so this is just going to be units squared. And that is it for this one. So it looks very complicated, but it ends up pretty nice because all kinds of stuff cancels out. In general, you can't necessarily hope for that, but for a lot of the book problems, they tend to work that way. So that's it for the test review. Please let me know if you have any questions. Otherwise, this is Dr. Lennon signing out.